Hey folks, today we're going to be looking at our second position time graph, and that's called a velocity time graph. And this is really a follow-on from what we've done the last two lessons, which was looking at displacement. So really similar axes, very similar concept, but instead of displacement, it's all about velocity. Just as a reminder, velocity is a vector, so that means we've got a magnitude and a direction. An example of that could be 10 meters per second up. So we've got our magnitude there. It's meters per second, so meters divided by second. That would be our magnitude. And we have our direction. It could be up, it could be down, left, right, sideways. Now, when we're going to be doing our velocity time graphs, the problem we had with displacement time graph is you can't really just say, well, it's left or right or up and down. We can only sort of go in two dimensions. So we're going to do the same thing that we did last time, which is we will say that positive and negative are both directions. Okay, so there's no such thing as negative speed. You can't go negative 10 meters per second. But if we talk about it as a direction, 100% you can say negative 10 meters per second, because that might mean you're going negative 10 meters per second to the left, or you're going down, or something like that. So just a reminder that I'm going to be talking about positive and negative in this sense, and it just means a direction, okay? And that just means they're in opposite directions to each other. Now, what I think will make it easier to explain a velocity time graph and show you how to do them is just to show you a really quick video on how a bottle rocket launches and how it sort of behaves. And it's very interesting to watch because this is actually something that we'll do later on in the semester. It's actually the highlight of the class. I guess that's why many of you may have picked the subject. But this rocket performs pretty well. You'll have a look at it, but might watch it a few times, but we'll see exactly how it sort of behaves. All right. So there it goes. Watch it one more time. The I guess one thing I just want you to pay attention to in this is, first of all, what's the direction that this rocket is going, and how fast do you think it really is going to begin with? So these folks did pretty well. I have seen a lot higher. It really depends on how much you push it. But there was a few things that we could pick up. Okay, I'll write a few things down here. So the first thing is the rocket goes up, doesn't it? It starts by goes up, and it is fastest at the start. It's going up, it's fastest at the start, and it will start to slow down. Now, at some point, it will reach the top. Now, this might not make sense straight away, but I'll convince you later that when it reaches the top, it's not moving for a moment. For a single moment in time, and I'm not even saying it's a second. A second is way too long. But at some point, like right there, it's not really moving. It's like it's almost stationary. It's not going up and it's not going down, if that makes sense. This one's a little bit tricky because it's going slightly sideways all the time. But in terms of just going up and down, it will reach a point where it is no longer going up and it's not going down, and then it will be sort of a transition. So then it starts to fall. So we'll go say rocket goes down. Now, it's probably going to be fastest when it reaches the bottom. I don't want to complicate things. I think we'll just leave it for 4 things at the moment. Okay. So let's see what this graph would look like. One thing that we would like to do is When our rocket goes up, we're going to call that positive. And when it is falling down, we're going to say negative. Okay? Are there any other few things? I suppose one thing that might help us is it looks like when we launch it. Where is it? Oh, here we go. So we launch it at 11. We launch it at 4, and then that's about, where's that? That's about 3 seconds, and I think it takes about 3 seconds to fall. So it's about 3 seconds here, and it falls down, it's about 3 seconds as well. Okay, so when we're going to draw our graph, we'll get our x-axis here. Pretty straight line, that'll do. And our x-axis is going to be time. Now, if we're doing a displacement or velocity time graph, x-axis is always time. So that's an easy one to remember. The y-axis, though, that's always going to be a little bit trickier. And that is going to be our velocity. And we'll put that meters per second. Have your units there. It's really important when you're labeling your axes as well. Don't just put a shorthand. Don't put V. It's always tempting, but you got to imagine the readers having a look at it. Now we said this whole thing is going to take, I think it's about 6 seconds overall. So we'll go 6. I think that's about halfway. That's 3, 4, 5, 1, 2. Yep. And you can notice, this isn't perfect. So if you're ever doing these in your book as a problem, don't stress about the details. It's all about sort of how fast things are going and things like that. In terms of are you actually demonstrating what is required, which is interpreting the graph, just drawing one. If I was to say, okay, you've got, I don't know, 30 minutes to do one graph, then by all means, get your ruler out and be super, super careful. But at this stage, we can sort of eyeball it, and that's all right. Now I've got my velocity, positive 10 to 30, and then we've got our negative velocity, negative 10 to negative 30. Remember, that just means it's falling down. I might just write that here on the side. So it's down. And in the blue, it's going up. Okay? So, our first point is that the rocket starts at 0. It's just on the ground. It's not moving at all. It's not going up, it's not going down, it's just staying there, right? But then, really quickly, it goes up to our maximum speed, and we're just going to say that's 30 meters per second. It's not quite right, but I reckon if we just eyeballed it, maybe it went up to 100 meters or so. But let's say it went up here, maybe it took half a second. It's probably even less because they go really quick. But it goes up to 30 meters per second. And let's just say it just maintained that sort of positive 30 meters. Okay, for about another second. So about 1.5 seconds into this thing. So it's going really fast. So it started at 0, it accelerates. Acceleration is a change in velocity over time. And then we're going at 30 meters per second, upwards, positive. And then it starts, so that's our first part. We've done that. Faster at the start, 3 seconds, cool. And then it starts to slow down, I guess, because it's faster at the start. So I'm just going to sort of do this here. What's happening is it will, I might do it in blue here. The white's not going to really work. It will start to slow down, okay? And it needs to reach the top, not moving, at about 3 seconds, okay? So what's happening is it starts to slow down. Now this is the trick, okay? If this was a displacement graph, you would say, oh, it's moving in a negative direction here, right? Because that's a negative axis, that's a negative gradient. But we're talking about velocity this time. So it's not a displacement graph. Even though this is a negative gradient, they're still got a positive velocity. They're still moving in the positive direction. And this is one of the biggest hurdles it comes to when interpreting these graphs. Everyone, including myself when I was learning this, will always make this problem. You'll be like, oh, now it's starting to fall, but it's not falling. it is falling like past this point, and I'll show you. Okay, so I'm going to do this in orange. We actually, let's go. It reaches the top, not moving, and I'm going to put that in a big green over there. And then the rocket falls down for another 3 seconds. And let's say it's going, and then straight up because it hits the ground, okay? So it's just going to hit 0 meters per second. So let's just say this, all right? This is fastest up, and then this is slowing down. Slowing down does not mean it's changing direction, right? It's still going in that same direction. Here we have the top of the arc, or whatever you want to call it, okay? If you do quadratics, I think it's called the inflection point. And then this part, this is when we are falling, okay? And then we hit the ground. So there's a few things, like I guess I've explained, but I'm just going to go through it all in one go. The higher like the velocity is on this, that means the faster it's going, okay? Negative gradient does not mean that it's changing direction. If it's in this positive space here, if it's a positive velocity, it's still going in that direction, but it might be slowing down, okay? If it could be slowing down, now it's speeding up, now it's slowing down or something like that. I'm not sure what would be that. Maybe just be someone running and stopping. Here, we are falling. And just think about it over time. And like, look, it's velocity. Okay, so it's 0 meters per second. Now it's 10 meters per second. Now it's 20 meters per second. Now it's 30 meters per second. So it's actually getting faster. When you drop something, it starts off slower, then it starts to speed up over time, and then poof, straight away. It's not really 0 seconds, but it would be like 0.000 whatever, 1 second. It hits the ground instantly. It hits 0 meters per second. Has no velocity because it's stuck in the ground. Yeah, hopefully that makes a bit of sense. The biggest hurdle, just to remind you guys, is you will get this confused with the displacement time graph. So always check the y-axis first before you even look at the questions or the problems or anything like that. They'll always ask you questions and stuff about this graph or whatever. Check out what the graph is to begin with. Okay, get your headspace around that first. Hopefully that makes sense. Peace out.